Welcome everybody. It is a great pleasure to celebrate Richard Feynman's birthday with this appointment of the GGI lectures by young researchers. So this week we have two lectures, the second one being on Thursday, again at 4 p.m. These lectures will be given by Luigi Tizzano, who is an expert in quantum field theory and currently a postdoc at the Simon Center for Geometry and Physics at Stony Brook. He will talk about some aspects of generalized global symmetries and anomalies. Before starting, let me remind you that this is meant to be an informal meeting, so please feel free to unmute yourself, intervene, and ask questions. Okay, that's all. So Luigi, if you want to start, the stage is yours.
Yeah, let me share my screen. Can you see again?
Yes.
Okay. Okay, so thanks a lot for the introductions and for inviting me. So I'm very happy to give these lectures, and I want to start with a disclaimer. This will be very informal, very introductory lectures on certain aspects of global symmetries and on certain new developments in quantum field theory. So maybe some of you already work on this topic and have heard similar lectures already. So in that case, feel free to decouple if you are not interested. But yeah, I hope that these lectures will give you a taste of what is this new thing that people are interested in and that they are talking about and why somehow we care about it. And maybe that with these lectures, you'll be able to understand more advanced papers on the subjects and maybe do your own research on the subject. So, okay, so let me start. And okay, so we'll start a little bit, maybe slightly more abstract, but then we'll try to drift right away into examples and more concrete things. And again, just please feel free to interrupt me anytime that you want to ask questions. So, okay. So the idea, so the goal that we have in mind is to understand some recent developments which are based on the role of global symmetries. So in this talk, I will be interested for basically almost all the time about internal symmetries, which have a well-defined action on the Hilbert space of the theory. So this is what I mean by global symmetries. And it turns out that recently we understood that there is a way to formulate all global symmetries in a slightly abstract way, which will be very useful for the generalization that we have in mind. So this is really a key property that we're going to use a lot in these lectures. So we will always think about global symmetries as in the following way. So I will call them often zero form global symmetries. So these are just the ordinary global symmetries that we are used and love in quantum field theory. I will denote them by a group G and with this superscript 0. So this 0 indicates the form is linked to this 0 form. And we will think that 0 form global symmetries, for the way I want to talk about it, are associated to a topological surface operator of codimension 0 plus 1, so codimension 1. And I'll denote this object by U of sigma. Sigma is some surface of dimension d minus 0 plus 1. Okay, so this is just a very abstract way to think about a global symmetry. So an ordinary global symmetry, we will always refer to it as the action of some topological surface operator of codimension 1. And what do I mean by topological? So topological means the following, that imagine that we are, so basically it means the following, that this operator U of sigma is independent of small, quote unquote, deformations of sigma. And let me try to define for you what I mean by small. So imagine that we are in a path integral situation. Sorry, my drawing is bad. So this is some surface sigma, which is the support of my topological operator. And then what we want to do is to deform this operator sigma so imagine that we kind of cut through here, and then we do some deformation delta sigma. So any correlation function of this operator U sigma, which involves deforming sigma by some small perturbation d sigma, will not change the value of the correlation function. So this is what I mean by independent. But I'll tell you now what I mean by not small, or so this is a small deformation. A not small deformation will be some deformation. Imagine we have this operator supported on sigma. And imagine that somewhere here at the point x, there is some operator O of x, and this is a local operator. Now, if I try to deform my surface and somehow I want to cross this local operator, this will not be a small deformation. So anytime we try to have a correlation function and we try to deform the position of this operator to cross a local operator, then this will be picked up by the correlation function. So in this case, in the independent case, we don't see any change in the correlation function, and that's my definition of topological. But if we cross a local operator, this won't be completely topological, and the correlation function will measure the action of this operator. And so, okay, so now this sounds like a very abstract thing, and like, you know, we just want to talk about ordinary symmetries, and you might think like, why the hell are we doing this? But it turns out that we are completely used to this concept, even though we never discuss it in this way. So let me give you an example. So we have, imagine standard U1 global symmetry. So U1 0 global symmetry. And this is, it's obvious that because of the Nether theorem, there is a conserved local spin 1 operator, which is J mu. It's conserved, so it obeys the equation d mu J mu equal to 0. And now we need to construct out of this operator a topological surface operator. So how do we do that? First, we define a charge. What is the charge? Charge is defined through taking a codimension 1 surface, so a space slice in Lorentzian signature, where we would integrate star of j. So this defines for us the charge under the U1 symmetry. And we would then have, naturally, the notion of a topological surface operator by just exponentiating this charge. So this object is the one that implements the action of the U1 symmetries on local operator in whatever theory have this global symmetry. Now, so you see, basically, when we think about continuous symmetry, this is very standard for us, just we probably never really thought about it in this way. But the catch in this story is that so important. So if you have a discrete global symmetry, so neither theorem doesn't apply. So there is no conserve local spin one current, clearly. There is no conservation law out of these symmetries. But very importantly, the notion of this topological surface operator is still valid. So there is nothing that stops us to define these objects, even though there is no conserved current for these symmetries. And this is extremely important. It will be very useful in various things that we'll discuss through this lecture. And okay, so now let me try to tell you how does, so then the natural question is we have this operator, but we want them to act on local operators. So how do they act on local operators? So the action of U sigma is the following. Imagine we have U sigma, and then we have some local operator OX. What does it mean? It means that at some point X, we will surround this point by this codimension one operator. And the idea is that because this operator is topological, we want to shrink down this operator so that it becomes a very, very tiny ball around O of X. And we will say that once we have this situation, we can still think about this as some kind of local operator, but now up to some phase or some group element. So this will produce for us the action. So you implement the symmetry that acts on this operator. So in what I'm gonna do now, I will always denote also a label for this operator where, so G is a group element. So I'm labeling each of these surface operator by the action, by this group element. And so that means that whenever they act on a local operator, they spit out another local operator up to the action of this element G. And this is totally standard. Again, if we go back to the Noether example, we would act with U of G, we will spit out something multiplied by its charge. And also another completely standard thing that we might want to do is just take products of these objects. So product rule. So we would have an operator UG of sigma, d minus 1, and then another operator UG prime of sigma d minus 1. And we want to act on the operator O at point X, and this will produce for us something like G prime, G. And this is standard again, because I can take an operator, surround it by this surface sigma d minus 1. Sorry, let me surround it by the UG prime of sigma, and then surround it by another operator UG. And so first I'm gonna shrink this surface. I'm gonna have the action of UG on O. It's gonna spit out the G prime times O, and then I'm gonna shrink down also this one. Okay, so these are completely standard thing. And so basically let me recap what we said. So when we have a G0 symmetry, we will have this operator UG of sigma d minus 1, which is topological. And we will say that G labels a group element. And in particular, if G labels a group element, there also will be an invertible element. So clearly, there will be an invertible element. Meaning that if I act with U of G, I can also undo that action by acting with the inverse topological surface operator. So I can undo the action of a global symmetry in this context. But here there is another comment which I want to make, but then I'm not going to talk about this, I think, for the rest of my talk, but just to give you an idea about something that could be possible. So when I do this axiomatic definition of these surfaces, nowhere it is required that these topologically surface operator are labeled by group elements. In fact, as a matter of fact, we now know that there are objects which are not labeled by these group elements and that implement certain other generalization of symmetries, which basically the only way that you can define them is through this topological surface operator. And in particular, this symmetry cannot be undone by some inverse. And so for this reason, this is a very important comment if you care about these things that are called non-invertible symmetries. And we are starting to understand more and more of these objects, but this is kind of advanced story. So let's go through first the standard thing, which are the ordinary global symmetries. So for ordinary global symmetry, these surface operators are always labeled by a group element. And another important comment is that clearly an ordinary global symmetry, so this G0, can of course be non-abelian, as we are used. Imagine continuous chiral symmetry in QCD clearly is non-abelian, but and including discrete and non-abelian. So you could have some crazy crystallographic group of some finite order, and that would be fine. There's no problem with that. Okay, so now we know basically very abstractly what is ordinary global symmetry. So this is the most general way that we have to define it. And we are ready to do a generalization of this notion to something that's called a P-form symmetry. So and this is precisely this thing that everyone has been talking about so much in the last 5 or 6 years. So whenever you hear generalized global symmetry, this is precisely the kind of things we have in mind. Something called a P-form symmetry. So just before I move to this point, is there any question on the ordinary global symmetries?
Yes, actually I have two.
Yes.
So first of all, are you like implicitly assuming that you're like in Minkowski or Euclidean is not relevant at all? And
right now it's not relevant for me. I'm going but everything I did right now was Euclidean. So yeah, I had in mind a path integral way to implement this thing. So
okay, thank you. The second thing is that in any field theory, right? I mean, the charges are not uniquely well defined in a sense that, for example, only the charge at infinity is uniquely defined because, for example, in the Lagrangian, you can add a total derivative, right? And so if your sigma is not the whole of space, Q of sigma will change, right? So I'm asking if you can associate uniquely, like to the G0 symmetry, for example, this topological surface operator.
So maybe I can make this. I mean, okay, as long so yeah. So the charge, okay. You can have modification of sigma, and as long as they satisfy any deformation of sigma, as long as it's topological, will not affect any of these arguments. So if you wonder, if you're asking, does that mean that I have infinite symmetries? Is that your worry?
No, my worry is that in a Lagrangian, I can, for example, in a Lagrangian theory, at least I can add like always a total term, right? A total derivative term that will affect like the charge if I'm integrating the charge over a compact volume, not the whole space.
Yeah, no, right now there are no, okay, sorry, I haven't specified. I'm always working in, flat space-time. I'm not considering anything topological, any topological abstractions of any kind.
Okay.
There are some, okay. If you want to talk about compact spaces and things that might have a boundary, then there are a bunch of things that should be added, but let's not go into that right now. Maybe we'll save it for a discussion at the end, okay?
Yeah, I mean, I was not referring to that, so maybe I didn't explain myself sufficiently, so maybe let's discuss it later.
Yeah.
Thank you.
Okay. Okay, so we just want to generalize this story to P-form symmetries. So again, if we have a GP symmetry, what is this going to be? It's going to be associated to a topological surface operator of codimension P+1. So it's going to be this UG of sigma D minus P+1. Okay, and again, these subjects, although it's slightly, okay, so for example, imagine that we have a G1 symmetry, so a one-form symmetry. For example, it's the action of UG. UG will be some codimension to surface operator acting on what? Acting on a one-dimensional line supported on a line gamma. This is a line, so you have some line gamma, and then you kind of surround it by, you surround it by this operator UG of sigma D minus 2. And of course, you could keep doing this for any GP just by having the right codimension object. And of course, we can again do the product rule. So again, we can have UG of sigma D minus P+1, UG prime, and that will give, well, let me just write it like this. UG prime sigma. Oh. Yes, and so again, we could have, for example, in the example of a line, we could have a line, and then we will surround it by two UG prime, and we can shrink first one and then shrink the other. And so now in the structures that appear in generalized global symmetry, so this kind of rule that I'm discussing lead to the following statement, which is somehow a corollary of this structure. And okay, so I'll give you the statement. Claim GP symmetries are necessarily abelian. So this is actually a fun statement to try to prove, and so it's all based on just some topological properties and on the codimension of this surface operator. So I leave it to you to figure out why is this the case, but it will be very important for us. So contrarily to ordinary global symmetry, higher form symmetry will always be abelian. They could be discrete again or continuous, but they will always be abelian. So just try to figure it out on your own. It's a fun thing to do. And in general, the other statement is that a GP symmetry acts on objects of dimension P. So if we want to have imagine that we want to try to think about this in Lorentzian, so in a way that these UG implement an action on the spacetime, then clearly zero form symmetries acts on particles, one form symmetries will act on strings. As a matter of fact, there are very interesting examples of theory which have this strings excitation. We're going to talk about them. And then, you know, two forms will act on some extended configuration that looks like, I don't know, sheets, etc. So there is a way to think about all these objects, I mean, up to a certain dimension, if you into some more familiar thing that we might understand in the Lorentzian interpretation. Okay, so let me give you an example now of one form symmetry in a very, very basic type of theory. So probably this is the simplest example. Which is Maxwell theory in D equal 4, okay? So that's fairly standard. We have so in we can just set up the problem in the following way. There is an abelian field strand that I denote by little f. It's D of A1, where A1 is the electric gauge field of the theory. And by the Bianchi identity, we know that D of F2 is equal to 0. This falls from the Bianchi identity. And we also know that D star of F2 is equal to 0 by the equation of motion. This means that we can define two independent one-form symmetries. And let me show you how. This is just a slight generalization of the Noether example we did before. There will be an electric current, G, which now has two indices. So it will be a two-form current, which is associated to F2. And clearly, we can define its electric charge through this codimension D minus 2, so codimension 2 topological operator. So we would integrate over sigma 2 star of JE, which is the integral over sigma 2 of F2. Sorry, of, yeah, star of F2. And clearly we know what is this. It's just this is the transverse electric field out that we would measure out of this surface sigma 2. But then we also have another current, which is the magnetic one, which is proportional to star of F2. And again, we can define Q of M as the integral over sigma 2 of star of JM2, which is the integral of sigma 2 of F2. And clearly, we also know what is this. This would be the magnetic field, which is piercing this sigma 2 surface. Okay, so if generally we will denote these symmetries by, sorry. In the following way, so there is a U1 electric one-form symmetry times a U1 magnetic one-form symmetry. And what are the charged operators under this symmetry? Okay, so question. What are the charged operators? And we also know what are they. They are basically line operators, or maybe defects. And so let me first think about the electric ones, which are the Wilson lines, or these are the same as infinitely massive electric probe charges. And how do we think about it? So imagine we have this object, it's some Wilson line, which is supported on a curve C, and it's surrounded, so my drawing is a bit bad, sorry, by this operator U sigma 2. And the Wilson line is defined in the following way. It's the exponential of I Q integral of C of this electric gauge field A1. And here, Q, remember, is an integer because we are talking about a U1 group. And so if we act with Q on W, this will spit out Q times. So this is exactly the action that we were defining before. And in order to define the magnetic line operator, that's slightly more abstract, but we also know what are they. These are the magnetic, so these were the electric. And then we have the magnetic. So the magnetic are called Tooth operators. They do not have a simple description in terms of local degrees of freedom like the Wilson line, but we can denote them by T of Q tilde, and you basically define them. These are defined as some disorder operator. And by this, I mean that if something like this appears in the path integral, you would have to give a prescription for how to perform such path integral. It's a bit abstract, but again, they will be supported on a line C. And there is some magnetic surface operator. And again, the action of QM on TQ, sorry, will be of the following kind. So one way to, another, like an alternative way is that to think about this as some kind of singular Dirac monopole. In this simple example. Okay, so basically that's the structure. In Maxwell, there are two one-form symmetries. They are both abelian, as we say, and they are associated to the electric and magnetic currents, which are conserved for trivial reason, as we know. And so this is somehow the basic structures of higher form symmetries. And later we will see also other applications. So is there any question on this stuff?
Yeah, sorry, maybe very naive one.
Yes.
From the definition you gave us before of QM and QE, how
Yes.
do we see that QE applied to WQ give us Q times W again?
How do I see that? Okay, that's a good question. So, you know, basically the idea is the following. You see how, so when I write something like this is, or is the exponentiated version of QE. So it will be this topological surface operator. And in this context, it will be constructed out of this current. So when you write any path integral, you will write this inside a path integral, okay? So the Wilson line is constructed to the electric gauge field, but also the current is constructed to the through this electric gauge field. So in the path integral, you will have to take basically OPs of these objects, and so these degrees of freedom will combine.
I see, thanks.
Okay, so now once we introduce a concept of global symmetry, whether it is generalized or not, there is another concept that comes along for the ride that is very important, and I'm gonna say a few words about it, which is the concept of symmetry breaking. So we all know and love that ordinary global symmetries can be spontaneously broken. And what I mean by that, I mean that in the situation where there is a spontaneously broken symmetry, it always exists. O is a local operator such that its expectation value is different from 0. And this operator OX is charged under the G0 symmetry. And in fact, this object O of X is called an order parameter. This is very standard in the study of spontaneously broken symmetries and phase transitions, and I'm sure you are used to this notion. So now, whenever the order parameter has a non-zero value, we would say that the symmetry is spontaneously broken. Now, there are two consequences of spontaneous breaking, which depends on whether we spontaneously break a continuous or a discrete symmetry. So it's very general. So spontaneous breaking of G0 imply the following thing. So if G0 is continuous, spontaneous breaking of a continuous global symmetries implies that we will find in the low energy description, there will always exist massless Nambu-Goldstone bosons. This is completely general. And this will always be true, provided that the dimension of the spacetime is greater than 2. However, if we break a discrete global symmetry, the situation is different. There are no Goldstone bosons for this breaking, but what we find is that the low energy description of the theory has more than one vacuum. So we call this situation degenerate. So you'll see something that have like a potential with 2 ground state, for example, or more. So sometimes you also hear people talking about this situation by saying that there are super selection sector. So often maybe you heard this statement. That's what it means. It means that there is a degenerate ground state and there are different vacuums. And you could also then study the theory that tells you how to tunnel through this vacuum by studying domain walls and things like that. All this physics, which is very nice, it's always associated to the spontaneous breaking of a global discrete symmetry. Okay, so that's just very general. Okay, but we have just introduced higher form symmetry, and so we need something similar because higher form symmetry, exactly like ordinary symmetry, can be spontaneously broken. So for example, let's think about one-form symmetry. So for one-form symmetries, we need to define what we mean by spontaneous breaking of this symmetry. And so certainly we need a new order parameter. And that's the idea is the following. So imagine, so what could this be? We sort of know that already. So we take some line, imagine that this is a big line gamma. And you could imagine, for example, in the example of Maxwell that we had before, that this is some big Wilson line. Sorry, loop. It's closed, so I'm taking it as a loop. And we would say that, let's call this omega gamma, sorry, W gamma. Then again, how is spontaneous breaking here is gonna work is the following. We will say that if the expectation value of this object is not equal to 0, we will say that this situation leads to a one-form symmetry, spontaneous breaking. Okay. So if we take this big Wilson line or some general line operator and we try to compute its vacuum expectation value, if we see that this is not equal to 0, we would say that the one-form symmetry basically of that system is acted non-linearly in the vacuum and it is spontaneously broken. But this gives us some interesting thing to think about, which is what happens when the one-form symmetry is actually preserved. So it's not broken, but it is unbroken. So imagine that a one-form symmetry is unbroken. So by this definition, if it's unbroken, its VAV is 0. But one way that we could do this is just to imagine that the vacuum expectation value of this big Wilson loop scales with the area. And we are completely used by this when we study strong interaction. So this means that we associate an unbroken one-form symmetry, very general, to a line operator was, let's say, area surface. Sorry, was this big area surface as 0 VAV. But we have so this tells us that whenever a one-form symmetry is unbroken in the vacuum, we will associate this to a confining vacuum. And this is very useful because in certain theories, not all theories that we know of, but many and useful ones, this notion of one-form symmetry and the fact that the theory preserves it in the vacuum gives us some very crisp way to define what we mean by confinement. So this is a useful thing to have. But, okay, so this is one thing, but then you could ask me, what if we break, so we spontaneously break a continuous one-form symmetry. So if it's not a discrete abelian symmetry, but it's continuous, like in Maxwell, what would that imply? So in the ordinary symmetry before, we said that if G0 was continuous, we would expect some Nambu-Goldstone bosons. So the idea is that here we would need to have something very similar. But now this higher form symmetry have currents with more indices, which are not gauge fields, but they are not spin 1, but higher spin. And this means that, for example, in the context of one form symmetry, the Nambu-Goldstone boson is actually a massless, well, it's a photon. So this means, so if the low energy degrees of freedom is a photon, it means that the theory in the vacuum at low energy, it's in a phase where you have a freely propagating photon, and this phase is a Coulomb phase. So in particular, it's completely deconfined and it's free. And this is very different because remember that, again, here, ordinary symmetry leads to scalars. So these Nambu-Goldstones are scalars in the infrared. But for higher form symmetry, you have these objects that potentially are massless higher spins excitations. And finally, there is a third option, which is very interesting, which is when you break spontaneously a discrete one-form symmetry. But okay, so this is very interesting and very rich. And so we will discuss this in more detail later, not right now. But this will give rise to many options. And so we have to discuss it with some more details. And so this is one reason why people suddenly got interested in this topic. It's that because you define symmetries in this way, you have new order parameters to understand, and you have this way to try to define a confining phase or Coulomb phases. So you have a way to understand more properties of gauge theory phases by thinking about these generalized global symmetries. So this is highly non-trivial. And so that's one reason why it is useful to think about these symmetries. Okay, so now I'm going to move to a new topic, which is very related, but let me ask if anyone has questions on this. Okay.
Yes, sorry, I have a question.
Yes.
So there is this Coleman theorem that we cannot break continuous symmetries in less than 2 dimensions.
Exactly.
But for the P-form symmetries, is this the same? We have to be above 2D? Or?
That's a very interesting thing. So this happens in higher form symmetry. There is a version of the Coleman theorem that holds for D greater than 3. And this is very interesting. I actually, so this is the Coleman, so the Coleman higher form holds for D greater than 3. And there's a very cute paper by a student at MIT called Ethan Lake, who who proven this theorem. Well, he proved it with very similar arguments. So you can find this paper. Yeah.
Okay.
Any other question? Okay. Now, the idea is the following. We defined a set of symmetries, but now we need a much more important statement, because in a theory, having a symmetry, well, it's an important fact to know about the theory, but we need something much more important, that is understanding how to couple a symmetry to our theory. And so in order to understand these kind of things, we need to discuss the coupling to background fields. So, okay, so let me just go back. Let's recall this fact. We said that whenever we have a GP symmetry, so let's for the moment assume, let's assume that G is continuous. So we said that a G symmetry implies that we have a P+1 form current JP+1. And whenever this thing is true, there is something that we can always do, which is the activate a minimal coupling. What does it mean? It means that we're going to turn on an interaction in our original Lagrangian, where we have a background field A, P, sorry, let me put it here. So this is a P+1 form gauge field. And in particular, it is a background. So it is non-dynamical. We are not summing over this field in the path integral. This is some source that we are introducing in the action to make manifest the coupling to the global symmetry GP. This is extremely important. Okay, so, and then there is this standard thing that is, okay, so that the current satisfy a conservation equation, which is D, well, let's write it like this, T star of JP+1 equal to 0. And this would imply that the coupling, the minimal coupling, is invariant under gauge transformation of the following kind. Okay, so this is completely standard. And so then the interesting thing to do is to study basically the free energy of some quantum field theory as a function of these background sources, and to understand basically how it reacts, what's the response of this free energy upon doing some gauge transformation for these background sources. So we want to think about the free energy of some theory as a function of these sources. There could be many sources where basically, roughly speaking, f is equal to minus the logarithm of the partition function. Okay, and so because of what I said before, that the conservation equation implies that the couplings are invariant under gauge transformation, the idea is that you would imagine that gauge invariance implies that if you take the free energy and you have a gauge transformation of this kind, and then that the gauge transform free energy is basically equal to the free energy as a function of the source. But the crucial point is that this is not always true. It is very important. So the fact that the free energy, that some simple equation like the one above doesn't always hold is extremely important. And we'll see why it is important. It is important because, so this is not always true, but there is a statement that we can make true in QFT for any kind of QFT, even though it might be very complicated. So what is always true, so this is always true, is that you can compute the free energy in some way and then compute it in some other way and take the difference. And it is always true that the difference between these two quantities will be equal to the integral of some local functional of the sources. And sorry, this thing is called a counter term. So this is a completely general statement. In any QFT, the only non-computable contribution are the contribution of local counter terms. So you could compute a free energy using various schemes, whatever schemes you like. And if you compare two of them, the difference between these different schemes will always be a counter term. And so these objects are always going to be present. So as a result, one could imagine the following thing. So we just said that F is defined up to counter terms. So the idea is that we could add a local counter term, say L local, to the original free energy in order to restore gauge invariance. Okay, so that's natural. We will go back here. There is this function f. We could say, okay, I'm going to add a piece, which is a local function of this curly A inside here. And so maybe when I do the gauge transformation of that, combined with the gauge transformation of f, the two of them cancel and we get something completely gauge invariant. That's like a natural thing to imagine. But the catch is that this procedure of adding local counter term to remove, to restore gauge invariance, again, the catch is that this is sometimes impossible. Okay, so there are certain situations in which there is the transformation of this background field spits out a piece that you cannot cancel in any way by adding some other stuff which is local to the original free energy. And if that's the case, we would say that the symmetry G has a 't Hooft anomaly. So a 't Hooft anomaly for a symmetry G is such that there is no way to add a local counter term. To restore gauge invariance. Okay, so this is the very general definition, and let me make some comments about it. So you will sometimes hear also the following statement. This is an alternative definition that you might have heard already and you know about it, that a tooth anomaly is an obstruction to gauging the symmetry GP. So if we have this symmetry, we just saw that as when we couple it to background field, it will spit out a non-gauge invariant piece. And so if we were trying to gauge that symmetry, which means we were trying to render the gauge field local, this would be a problem because we wouldn't have well-defined interaction in the action. And so an alternative way to say that a theory has a tooth anomaly is to say that the symmetry G cannot be gauged consistently. Okay, and again, and this is very important, whatever I said before, it's completely valid also for discrete symmetries. So this is very subtle though, because when we have discrete symmetries, one need to make sure, one need to define carefully what it's meant to add a local counter term. So what is meant by this procedure when you have a discrete symmetry, because you have to write actions that are local for basically background fields for discrete symmetries. And in general, physicists always know how to do this because we are very brave mathematically, but this also requires some kind of mathematical machinery. So mathematician came up with a concept that is called an invertible field theory. And then this type of notions have always been used very, very frequently in condensed matter physics. And so this is what goes under the name of symmetry protected topological phases. So just for our high energy point of view, a symmetry protected topological phase would be a way to introduce a counter term for this non-invariance under a discrete symmetry. Okay, and just one final comment is that, as I told you, what is always, so we said that we can always add this, so we can always add this sorry, can you hear me?
Sure.
Yes, loud and clear.
Yeah. So we can always add something local to the free energy. Let me denote it with a tilde so that, okay. Now, the point is that not everything that, so what is the root of the problem in this idea of the tooth anomaly is that not every L local that we add to F will be imagine that we act. So now we have the system, which is F plus the integral of d xl local. Now, what we need to do is to act on this system with a gauge transformation dg. But not every functional that we had to cancel is, so not every, there is not every functional that we have to cancel will be the dg of some L local. So this is something we need to make sure this doesn't fall automatically. So imagine that this is the one that we need to cancel. And in fact, this idea of toothed anomalies boils down in mathematics to a cohomology problem. So there are very abstract ways to try and define and classify toothed anomalies by trying to solve this kind of cohomology problem. There are very interesting and formal things that people have been thinking about a lot on how you set up these things. And again, for discrete symmetry, this is also very interesting, and you need some sophisticated mathematical machinery that we're not going to go into today. Okay, so now we are ready to just do this let's just try to understand all this again with our working example, which is Maxwell. So example. Okay, so we have free Maxwell, which we want to understand everything about this theory. We want to beat it to death. So we are in 4 dimensions, and we said that there are two one-form symmetries. U1 electric and U1 magnetic. So then what do I want to do? Okay, so, and we have 2 currents. Okay, so now following what I said before, we want to introduce some background fields, right? So we will introduce these background fields that I denote by BE and M. They are 2-form gauge fields. And so under a gauge transformation, they shift in the following way. So this is a 1 form. Okay. And another thing which is very important is to recall that so Maxwell clearly has a dynamical field strength. Which is F2, which also changes under gauge transformation. So F2, what is F2? Is D of A1. A1 is the electric gauge field, and F2 is the electric field strength. So it changes under gauge transformation of the electric type. So F2 goes in F2 plus again D lambda 1 electric. Okay, and F2 clearly being an electric gauge field is neutral under U1 magnetic. Okay, so now what we need to do is exactly what I said before. We need to study the action of Maxwell in 4 dimensions as a function of the background sources. So I'll introduce the action is a function of, well, of the dynamical field strength and of the sources B2E and B2M. So how do we write this functional? It's 1 over 2E squared. Then we have F2 minus the electric 2 wedge F2 minus star the electric 2 plus I over 2 pi F2 wedge BM2. So this is the most general action of Maxwell as a function of the background field. And notice that this action S4 contains the minimal coupling. So there is the coupling BE2 wedge star JE2 plus dm2 star jm2. This is inside the action here. And this also, S4 also contains this term. And this term is needed, this is needed to implement the invariance under U1E. So if you want the kinetic term to be well defined under this transformation, you need to also have this term like that. Okay, now what's the goal now? The goal now is to perform gauge transformation of the background field, exactly as I told you before in the story of the 't-Hooft anomaly. So if I transform with B in this way, so this transformation of the electric one-form symmetry have the following consequences: that the first piece of this action, let me say, under this transformation, we know that this piece is invariant, but there is a problem here, that this piece here down here is not invariant. Why so? Because we can do the transformation, and this will change in I over 2 pi, integral of lambda E1, wedge dBm. So this is the non-invariance. Sorry. Under U1E1. So we performed a background gauge field transformation for the electric one-form symmetry, and this spits out a non-invariant term in the action. And notice that if we were doing the same with the magnetic one-form symmetry, the term that is non-invariant would be invariant because F2 is closed. And so it's very simple to show that that term would be invariant under the magnetic symmetry. So this is a problem because there is such non-invariance. And so the question is like, can you remove this? So question, can we remove it? And the answer is no. So there is no way to add a for the local counter term to cancel the non-invariance. In fact, the only way that I can kill that term in the action is not to add any 4-dimensional local counter term, but to kill that term, we need a 5-dimensional topological term, which I can define like this. So this is a 5-dimensional term, which is a function of these two background fields. And this is defined on a 5 manifold with a boundary. So the boundary of M5, it's our space-time M4. So this is where Maxwell is defined. Okay, so I have no way in Maxwell to remove such object, and that's a sign that there is a mixed 't-Hooft anomaly between the electric and the magnetic one-form symmetry in Maxwell, This is highly non-trivial. I mean, we really had to formulate the problem in this way. Although it's like a trivial example of a theory because, you know, there isn't that much interest in studying Maxwell, but you see that there is already a sign that when you study the theory as a function of these backgrounds, there are very interesting phenomena that can appear. And of course, one could say, okay, but maybe you could take the, so we could take this S5 and then basically integrate by part. And then, so if we integrate M5, the S5 by parts, we could then try to add something that lives on M4, which is proportional to, let me not do any mistakes, so to B2E wedge a BM. So you could say, I'm going to integrate the S5 by parts, and then I'm going to try to add something to see if actually it is completely true that I cannot remove that counter term in 4 dimensions. But you see, doing this basically amounts to this same as taking F2, taking the electric dynamical gauge fields and sending it to a new F2, which is the old F2 minus BE2. So you could do this thing here. So you take the old dynamical fields and then you redefine the dynamical fields by basically adding it this background field. But the idea now is the following, that while you will produce a term which is now invariant completely under the electric one-form symmetry, there will be an issue because you're going to have something which now does not transform under the magnetic one-form symmetry. So there will be a term that is, roughly speaking, I over 2 pi integral of lambda 1 magnetic wedge dBE. So it is exactly the same problem. You cannot disentangle the two transformations. If you try to save gauge invariance under the electric one-form symmetry, you're going to have problems with the magnetic and vice versa. This is exactly what we mean by a mixed tooth anomaly. So you have two symmetries, G1 times G2, and you cannot gauge one of the two symmetry without spontaneously breaking the other symmetry. Because if we try to gauge G1, there will be non-gauge invariance under G2 and vice versa. Okay? So Maxwell is a very beautiful example because it's a very simple theory that has higher form symmetries, that shows these non-invariance under background gauge fields, and that shows an example of a tooth anomaly. So it contains basically all the basic physics that will be useful for us in the following lecture. Okay, so I hope that this example was clear. And I would like to know if you have questions on the example or on anything I said before. Okay. If not, or if anything is not completely clear, I suggest you to try and do this exercise on your own. You can just take this action S4 and try to play around with the gauge transformation under the one-form symmetry. It's a very cute exercise. Okay. So now comes the final piece, which is why. So, okay, we said that, so the logical steps is that we now define what are GP symmetries. We said that GP symmetries can be spontaneously broken. We said that GP symmetries can couple two sources, and that GP symmetries can have toothed anomalies. Okay. But now the real question is like, okay, now we know all these kind of things. And so we would want to be also trying to understand why people are interested in the fact that these symmetries have toothed anomalies. So somehow in general, imagine that you have a symmetry, it has a toothed anomaly. Does it tell us anything about the symmetry and the underlying, sorry, does it tell us anything about the underlying theorem? Sorry, about the underlying theory. And so this is basically at the heart of the work by Tooth. So there is something which I'm going to discuss now, that is the Tooth anomaly matching. And this is really why there has been this renaissance of this kind of study in recent years, because for general ordinary zero form symmetries, the constraint of toothed anomaly matching have been studied in a lot of examples, in a lot of details, and everything has been known about it since the 80s. The new catch is that because we have these new symmetries, you can start and rethink about everything that we know about toothed anomalies, but using these new symmetries. And the idea is that when you use toothed anomalies for these new symmetries, you are gonna have new constraints on the low energy physics of various theories that are very interesting for, you know, physical application. So let me try to tell you why we are interested in this. So first of all, this is very important. Toothed anomalies obeys so-called non-renormalization theorems. Okay, so I told you that if you have a symmetry, it's some symmetry G, it doesn't matter if it's higher form or not. If GUV, so there is, sorry, let's say that you have some theory in the ultraviolet, it has some symmetry GUV, and GUV has some toothed anomaly. If GUV has some toothed anomaly, it means that there is going to be a local counterterm of the sources, which is multiplied by some coefficient KUV. So this will be some background fields for the UV symmetry. Okay, and so this KUV is also called, is the anomaly coefficient. So it's the toothed anomaly coefficient, okay? And a very, very important aspect is that, so KUV will be constant. So KUV is a constant because we need to ensure that the local counterterm is invariant under gauge transformation. So we have to be always able to integrate by parts these objects. And so KUV clearly has to be a constant. But now the important point is that KUV cannot be a function of any continuous coupling of the theory. So imagine that your theory TUV has some couplings like lambda1, lambda2, etc. So they could be, you know, the gauge coupling or whatever, certain masses or whatever, any couplings you have in mind. Imagine that this theory has it. So the very strong statement is that KUV, this anomaly coefficient, can never be a non-trivial function of these couplings. So you could imagine some strange situation where KUV will be a function of the continuous coupling, and it's a constant because it's going to take value at some of these. You evaluate on the value of some of these couplings, and that will give you a constant. This theoretically, this could be in principle possible, but this is actually, you can prove that this is impossible. Because the moment you assume that KUV is a function of this continuous coupling, you violate gauge invariance of the counter term. This type of argument, by the way, are used like a lot in many areas of physics. Maybe people have studied supersymmetry. This type of non-renormalization theorems are used every single day in supersymmetry, and they are exactly in the same flavor. So KUV cannot depend on this continuous coupling, so it's rigid, and it is very cool. So KUV is rigid under any deformation of the coupling, which means that whenever we have an RG flow, KUV is a very interesting quantity that we can track down to the deep infrared. So there is this object, it's KUV. It's given to us because we can compute this, it's the Tooth anomaly, so we know what KUV is. And we can track it down consistently in the infrared because there is no perturbation of the couplings whatsoever that could affect the value of KUV. So this is really the heart of the old argument by Tooth. And so you, in one sentence, you have to think that Tooth anomalies are good RG invariant quantities to study. Okay, now then comes this second point. So we now know that KUV doesn't depend on couplings and that it exists both in the UV and in the infrared, and it makes sense to study it. And the second point is that there is something called the Tooth anomaly matching principle. So it says the following: if a theory TUV as with some symmetry GUV as a Tooth anomaly, so if this theory has a Tooth anomaly, then you could flow to some infrared theory with some infrared symmetry group G. It doesn't matter what you do to flow to the infrared. If the ultraviolet theory has a Tooth anomaly, the infrared description of this theory must, and this is very important, reproduce the anomaly. So if you have some coefficient in the ultraviolet that you measure and then you flow to some infrared, there has to be a way to describe this in the infrared, even though the degrees of freedom of the infrared description might be completely different. The theory might be strongly coupled, there could be anything, but if the ultraviolet theory had this anomaly, it should be reproduced in the infrared. And so this is very constraining on the kinds of dynamics that the infrared theory can have. And so that's very interesting. And I want to make two more comments. before wrapping up, which is so we need to distinguish between two kinds of 't-Hooft anomalies. Okay, so there are two general families of 't-Hooft anomalies, and their implication for the infrared description will be different. One type is called an infinite order 't-Hooft anomaly. What does it mean? So an infinite order 't-Hooft anomaly is an anomaly for a continuous symmetry group. So G is continuous, and we are very used to this. These are all the anomaly that, for example, we study in ordinary courses in quantum field theory, where we have massless fermions and we compute triangle diagrams, and the coefficient KUV can be any integer, and the local counter terms are functional of the background sources, and these functional are Chern-Simons functional. Okay, so this is the most standard anomaly that we encounter every time in a QFT course. Okay, so G is continuous, and you have it's infinite order because basically the order of this K is infinite. It can be any integer. And then there is a different type of anomaly, which has surfaced more recently, which is the finite order anomaly. So it's the same. You have a 't-Hooft anomaly. Now G, in this context, G can be will be discrete, but could also be continuous. So it doesn't, this finite order doesn't distinguish on the type of group. What it distinguishes the anomaly is that KUV takes value in a finite group. So it's an integer, and on top of that, it takes value on a finite group. Could be Z2, Z4, ZP, whatever, but that's the idea. And so these finite order anomalies are very interesting, and they will play a very important role in the study of Yang-Mills theory in the next lecture. And also the infinite order anomalies are very important, and we studied them a lot in quantum field theories. But the two kind of anomalies leads to slightly different constraints on the infrared description of the quantum field theory. And that's the last thing I want to say for today. So let me just tell you about this topic. So again, we have some theory UV. It has some symmetry group GUV. And we have some RG flow to some infrared description. So we want to say what changes between a theory that has a finite order versus an infinite order anomaly. Okay, so these are the two basic statements. Statement number one is that if TUV has a infinite order anomaly, for GUV, this implies that the infrared theory must be gapless. So it doesn't matter whatever symmetry you are considering, if this ultraviolet theory has a 't Hooft anomaly, and that 't Hooft anomaly it's of infinite order, or more naively, if that 't Hooft anomaly is for a continuous symmetry, which is the case we are most used to, the infrared description of the theory must be gapless. It means it has a, this theory does not have an energy gap between the ground state and other excited states. For example, free fermions, it's the simplest example of a gapless theory. And of course, conformal field theory more generally could be interacting, are example of gapless theories. So if the ultraviolet has such an anomaly, the infrared necessarily is gapless. There is no escape from this. Now, the more interesting scenario is that TUV has a finite order anomaly. Now, which, for example, the finite order here, so as before, naively, before we said G continuous, so now imagine that there is some anomaly for some discrete symmetry, okay? Now there are three routes here that are different. So the first is that the infrared leads to a theory with a degenerate ground state. So exactly as in the spontaneously broken phase for a discrete symmetry, one consequence of this finite order anomaly is that the ground state of the theory is degenerate, so there are multiple vacua. Another option is that the theory is some kind of gapped phase, which is described by a topological quantum field theory. So TQFT. So it could be that at low energy, all local degrees of freedom are basically gapped out, and you just have some gap phase, which though is described by some non-trivial topological degrees of freedom, which are encoded by this TQFT. So for example, the TQFT could be Chern-Simons, or it could be some in 3-dimension, or it could be some more complicated topological quantum field theory in higher dimensions. So this is completely possible if you have a finite order anomaly. There's nothing that, you know, stops you from this scenario to be applied. And then finally, there's also a third option, which is exactly as before. There is also an option that the infrared is gapless. Okay, so there are 3 scenarios here, not just one. But one thing that is certainly true is that, okay, you could think that this scenario is kind of much more, it allows many more options, which is true. But there is one option that a finite order anomaly rules out completely, and that will be important for us tomorrow. So you could say point number 3. So if a theory satisfies point number 2, so if a theory has a finite order anomaly, it cannot be trivially gapped in the infrared. So what do I mean by a trivially gapped phase? A trivially gapped phase for me is a phase where there is a unique ground state and there's an energy gap above that ground state. And if you compute the partition function of that phase on any compact space manifold, you won't see any degeneracy. The partition function would be trivial. So an example of a trivially gapped phase, it's pure Yang-Mills at theta = 0. So probably the most important example of a confining theory, that at theta = 0, that theory is trivially gapped. okay? And one of the points that we are going to make tomorrow, well, not tomorrow, on Thursday, is that certain very important and very interesting theories that we know and love have finite order anomalies. And so these have important implication on the infrared description for this theory. So I think that this is a good point to stop. And again, I thank you a lot for your attention. And please feel free to ask any question now.
Thank you very much, Luigi, for the truly interesting lecture. So, are there any questions? There was the question from Enrico Andriolo, I think.
Yes. Yes, here I am. And what I was asking if the surface, the associate naturally to the symmetry, the topological surface operator, if that is the name, if it is uniquely defined. If I give you the group, uniquely define it. Because I was thinking that maybe you can add, for example, in Lagrangian theory, you can add, for example, total derivative in the Lagrangian. And so, for example, if you compute the Q over all space, then that is left invariant. But if you start computing the charge over a surface, which is not infinitely spread, then that maybe can pick up boundary, because you added something in the Lagrangian, right?
So I'm slightly, so, okay. So I understand that you can always add, I don't fully understand the connection. So, okay, I agree. You, on R4, you can always add some total derivative to your Lagrangian. Mm-hmm. But the way I define this topological surface operator have nothing to do with the Lagrangian or what you add to the Lagrangian. Mm-hmm. The only thing I'm doing is to say that you take some surface which you define in spacetime, and you associate to this surface in the spacetime an operator. Whatever modification you do to the Lagrangian of the theory is not going to affect that. So in fact, I'm slightly, even by what you mean by, so let me be more specific. I suppose that you say because you want to try to find some way around to modify how you find the current through the nether procedure. Yeah, I think there is no such a, so for example, I could just, so let's just go to a place where this argument would not hold, which is, imagine that there's no way for you to derive such current, like in a discrete symmetry. Clearly, the notion of a topological surface operator is well defined, and it doesn't depend on what you add on the Lagrangian.
Yeah, I totally agree with you. And so, yeah, I was thinking that, there must be a way to uniquely associate, right, this topological surface term. So,
well, there is one thing though that is slightly, okay, so, you could label, you could have, I'm just saying, you could have a topological surface operator and add to it another label in front of your definition, some parameter, and then think that each parameter implements a slightly different topological surface operator. So in that sense, you could have infinite amount of topological surface operator. But when you have a symmetry, I think it's it is always true that you can have this surface operator, and I have to think about it. Right now I don't know. I have to think about it, but I do not think that adding such total derivatives would affect in any way my argument.
I see. Thank you.
I'll try to get back to you.
Thank you. Maybe it's completely wrong. I mean, it's just my gut feeling. That.
Okay, other questions?
There's a question in the chat, Alessio.
Yes. I don't know, Luigi, if you want.
Yeah, I'm trying to read it. Okay.
It's a little bit long.
For the OneForm Symmetry max. I see. This is an interesting question. Okay. So he's asking if, well, it's a long question, which you probably everyone can read in the chat. Yeah. So what you ask, I would say there are other situations which are not Maxwell theory where you could have, yeah, these anomalies popping up at quantum level. So yeah, so in general, okay, it's not in full generality. So to answer your question, not all these anomalies will be necessarily manifest at the classical level. So there are examples where this is not the case. One example that it might be interesting, and maybe this is also another good exercise for next time, if you could educate yourself about this theory, and you could study U1 level K Chern-Simons. So this has action K over 4 pi integral of ADA. And you could repeat the entire story. So there are interesting questions. First question, how do we define higher form symmetries? How do we couple them, and is there an anomaly? Okay. So that actually will be an interesting example that unfortunately I don't think I'll have time even next time, but if you want to study it on your own, it's very educational.
Okay, so I think we can stop the recording, so we can leave some space for more informal questions.
Yeah.